In this video, I will concentrate on solving few problems concerning the motion of objects on the frictional inclined plane, and then I will be revealing the basic concept that will really be helpful. Subsequently, I will be producing more helpful videos in this aspect, so I will advise that you subscribe to this channel. Notice that anytime you're about to solve a problem concerning inclined plane, you don't need to memorize or cram the formulas. You just need to understand what will happen to an object that is on an inclined plane. Now, let's say you have something of this nature as the inclined plane. Okay, where this is the angle. Okay, let's say this is angle theta. This is the inclined plane. Okay, is the inclined plane. Alright, so let's say you place an object on the inclined plane of a particular mass. Alright, so naturally this object will slide down the inclined plane. Okay, if there is no friction. Why is it like that? This is due to the component of the weight of the object. So let's see that. As the object is being placed on this inclined plane, its weight acts vertically downwards. Okay, so we have its weight right here, and also there is an equal but opposite force to the weight, which is the normal reaction. Now let's say I place an object on this surface. This object will exert its weight vertically downwards, and then this surface will also exert force, an equal amount of force on the object but in the opposite direction, which is called the normal reaction. But this normal reaction is not always vertically upward, it is always perpendicular to the surface in contact. So it's a contact force. So the normal force in this case, it will not move in this direction opposing the weight of the object. It will rather move perpendicular to the surface at 90 degrees. This is the surface, so that means it will move in this direction because it has to be perpendicular to the surface in contact. Okay, so also this weight can be resolved into its horizontal and vertical components. So this is like just what we have right now. We have the weight of the object right here. So we may resolve the weight into its vertical component. So let's say something of this nature, and then we may resolve it to the horizontal components. So if I resolve it this way, I can also resolve it this way. So the horizontal component of the weight is what we always have at the parallel, at this point, which is parallel to the plane. Okay, so and this is just perpendicular to the plane, which is another component of the weight. And this component of the weight, which is perpendicular to the plane, is equal and opposite to the normal reaction, to the normal force, which is perpendicular to the plane. So they are both perpendicular to the plane acting on the object. All right, so let's say this is the weight with symbol W. If we resolve into the vertical axis, that will become, and notice that there is angle theta right here. That same angle theta will be the angle at this point. Okay, and this is due to alternate angles. The sum of the angle in a triangle is actually 180 degrees. So let's say this is the triangle. Let's say this is triangle ABC. Okay, so the weight coming down from this point we also form another triangle. So let's say the weight is coming down right here as triangle CDE. So let's say this is triangle ADE right here, and it can be extended into triangle B and C right here. So if I have angle theta right here, the angle here, if it is 90 degrees, this is the symbol of the 90 degrees angle. Okay, if this is 90, this will be 90. And then if this is any angle, let's say this is phi, this will also be phi. Okay, it means that the sum of these two angles has to be equal to 90. If this is 90, then phi and theta must be, the sum of phi and theta must be equal to 90 degrees. Now let's say there is another line right here. Okay, and that is the line that is perpendicular to the plane, which is the same thing as the vertical component of W for this diagram. So for us to know the angle which will be enclosed between this line right here, okay, between this line right here and this line, its vertical component, then we need to just say that, this is the plane and this is the perpendicular axis, and there is a particular angle right here which is given as phi. So for us to know the remaining angle, then we need to just say 90 minus phi, because it is actually this is actually perpendicular to the plane, and from this point to this point is phi. So to know the rest, then we need to say 90 minus phi, and don't forget that theta plus phi is equal to 90. So 90 minus phi will also be equal to theta. So we'll always have theta right here. Okay, so this angle here is the same thing as the angle right here. All right, so if I resolve this to this point, then I will have something of this nature. I will have W cos theta. Okay, if I resolve it to the horizontal axis, I will have W sine theta. Notice that W cos theta is due to resolution of vectors W cos theta and W sine theta, because I already resolved W into its horizontal and vertical components. This is what I have in that diagram. I have a triangle that looks like this. Okay, where this is the W, this line right here, and this is the vertical component of W, this is the horizontal component of W. Let's have the arrow right here with this arrow, and this has its own arrow right here as well, and then this is the arrow for the weight, okay, which is vertically downward. So, and then there is an angle here, angle theta. It's actually a right angle triangle from this point. Okay, so in order to find, let's say this is the horizontal axis, to find the horizontal axis with symbol WX, so I can make use of the SOHCAHTOA. Okay, from the SOHCAHTOA I have the one that is connecting opposite side, and this is the opposite side WX, that is the opposite to angle theta. Okay, so the opposite side and the hypotenuse is the sine, so I can say sine of theta is equal to opposite side, which is WX, upon W. So if I cross multiply, I'll have WX to be equal to W sine of theta. So that's how we arrive at this. Okay, and then for W cos theta, I just need to make the one with adjacent, because this is actually WY, which is the adjacent to the triangle. So I can make use of cosine. Okay, so that cosine of angle theta is equal to the adjacent, which is WY, upon the hypotenuse, which is W. By cross multiplication, WY will be equal to W cosine of theta. So that's how we arrive at this. So anytime you have an object on an inclined plane, the first thing that will happen to the object is that the object will have all these components acting on it. Okay, and then if the inclined plane has friction, then the friction will be opposite to the motion of the object. Okay, so we'll have the friction in this direction for this manner. But if it does not have friction, if it's a frictionless surface, then the surface will be without friction. Before I solve the practice problem, let me quickly take you through the concept, the differences between the static friction and the dynamic friction. Both are the types of friction. Okay, now let the friction can be static. Okay, it can be static and it can be dynamic or kinetic. Okay, if it is static, then it is acting when the object is not in motion, or when the object is in motion but at a constant velocity. So its formula is given as this: the less than or equal to the mil of s. Mil s is the coefficient of static friction, then the normal reaction. Ordinarily, frictional force is proportional to normal reaction. So if we remove the proportionality sign, we will need to substitute by equal to and a constant. The constant is called the coefficient of friction. But since we have two types of friction, then we consider it static and we also consider it kinetic. So the kinetic friction will be equal to the coefficient of kinetic friction multiplied by the normal reaction. Okay, the normal force or the normal reaction is what I described the other time, that is always perpendicular to the surface in contact. Okay, now notice that the static friction is an inequality. That is, it is less than or equal to the coefficient of static friction of the object multiplied by its normal reaction. So let's say there is an object on a surface, all right, which weighs, let's say the object weighs 100 newton. Okay, and then that means the normal will be n, which is actually equal to 100 newton. Let's say the coefficient of static friction of the object is equal to 0.4, that is the mu s of the object is equal to 0.4. Coefficient of friction, it actually ranges from 0 to 1 depending on the type of the material. So let's say this kind of material has this as its coefficient of static friction, and then this material has this as its coefficient of kinetic friction. Let's say 0.12. Okay, all right. So that means we can find its frictional forces, that is the Fk, the frictional forces, the kinetic frictional force, that will be equal to the mil of k, which is 0.12, multiplied by the normal, which is 100 newton, and that's supposed to be 12 newton. Okay, now let's say the coefficient of the static friction, it has to be less than or equal to the product, that is 0.5, multiplied by the normal reaction, which is actually 100. All right, so if you do the multiplication, then we should have something of this nature. So it means that I can have it as something of this nature. I can have it as coefficient of static friction is less than or equal to 50 newtons. Okay, now the notice the meaning of the inequality. It means that the static frictional force is less than or equal to 50. The static frictional force Fs, it actually ranges from a particular amount. It ranges from 0 to a particular amount, which is called the maximum static frictional force. Let's say Fs mask. Okay, let's determine if this object will move. All right, let's have the applied force. Okay, let's say the applied force is P. Okay, if the applied force is P, and then the net force right here. Okay, and then the coefficient of, I mean, the static frictional force, and then the kinetic frictional force right here. All right, so if let's say you apply a force of 0 Newton. If you apply a force of 0 Newton on an object, what is the frictional force? There will be no friction acting on the object, because forces causes motion, and if there is no motion, there will not be friction. Okay, because friction actually opposes motion. So at this point they will all be zero. Okay, the net force on the object will also be zero. Now let's say you apply a force of 5 Newton. Okay, if you apply a force of 5 Newton, with the object to move, this 15 Newton, if you apply any force greater than 50 Newton, you would have overcome the static frictional force. So if you apply a force of 5 Newton, the static friction in this case will also be 5, but the kinetic friction will be 0. Notice that the kinetic friction only in existence when the object is in motion. So if you apply a force of, let's say, 5 Newton in this case, which is supposed to move the object, it will not move the object because it is not up to it is not more than 50. It is not greater than 50 or equal to 50, so it's not going to move. The object will remain at rest. So it is remaining at rest because there is an equal but opposite force, and that will also be 5 Newton, not 50 Newton. If it is 50 Newton, that means if you apply a force of 5 Newton on the object will move backwards with another force of 45 Newtons. Okay, so that's actually impossible. So if you apply a force that is not up to the maximum static frictional force, the object will still remain at rest. Let's say you apply a force of 49 Newton. If you apply a force of 49 Newton, notice that the net force will still be 0. You apply a force of 5 Newton, there is a static frictional force of 5 Newton. So 5 minus 5 will be equal to 0 for the net force. If you apply a force of 49 Newton, it is not able to move the object. Okay, this is a force of 49 Newton that is being applied. The object will also exert, because the object has the capacity, the object will also exert a force, an equal amount of force in the opposite direction, which is also 49 Newton. So the object will not move. Okay, the kinetic friction will be 0. So the net force on the object is 0, since the object will refuse to move. But let's say you apply a force of 50 Newton on the object. If you apply a force of 50 Newton on the object, the 50 Newton is able, at this point, the object is ready to move. Okay, the object, since the object has the capacity 50 Newton, so the object will, the static frictional force will also be 50 Newton, and the net force will also be 0, and then the kinetic friction will be 0. Now you have already overcome the static frictional force. Okay, so you just, the force that you need to apply now is a force that will be more than the kinetic friction. So you can apply a force of, let's say, later you apply a force of 100 Newton. Notice that at this point the object is set to move. If I apply a force of, let's say, 51 Newton or 100 Newton, there will be no more static friction on the object because I already overcome its static frictional force. So I just need to, the frictional force that will occur in this place will be 12 Newton. So I will need to have 12, the net force will be 100 minus 12. Okay, and that's supposed to be equal to 88. Okay, that means 88 Newton force will be driving the object. Okay, now if you apply a force less than 50, let's say you apply a force of 20 Newton, the frictional force will be 12, is constant. Notice that the kinetic frictional force is constant at 12, so it will always be 12. So the force, the amount of force that will drive the object will be 8 Newton. That's 20 minus 12. So you for the object to move, you just need to begin to apply forces that are greater than the kinetic frictional force. So the 50 Newton force is the maximum amount of the static frictional force, after which any force applied more than the kinetic frictional force, the object will begin to move in the direction of the force. Let's say you have a very big stone on the ground. If you push this stone right here, okay, if you push this stone right here, it will be very hard at first to set it in motion, but when the stone is already in motion, it will be very easy to apply the force. It will be the force that will be applied at first to set the object in motion will be more than the force that is applied when the object is already in motion. Okay, and this is actually because static friction is always more than the kinetic friction of an object. So the force, that is the more force is needed to overcome static friction than to overcome the kinetic friction. So the object tends to require a lot of force in order to be put in motion than when it is already in motion. Okay, now the implication of all of this is that, let's say I have an object on a surface. Okay, let's say I have an object on a surface on an inclined plane that looks like something of this nature. If there is an applied force in this direction, notice that when I place this object on the inclined plane, there will be mg sine theta naturally. I already explained. Okay, and then if I apply a force of F, okay, let me say P, if I apply a force of P in this direction, which is up the inclined plane, there will be a frictional force that must oppose the motion, okay, which is Fr. Let's say that is Fr. Now the implication of what we have discussed is that for the object to move up the inclined plane, it means that P must be greater than or equal, okay, to the sum of the force that are opposing the motion, to the sum of mg sine of theta plus the frictional force. If P is greater than the addition of these two forces, it will be able to take the object upwards. And if P is equal, at the point where P is equal to the sum of these two, that point is the minimum point, is the minimum value of P with which P will be able to take the object up the inclined plane. Okay, and this is because they are in opposite direction. So let's solve the practice problem. An object has a mass of 10 kg. It is placed on an inclined plane at an angle of 60 degrees to the horizontal. Calculate the horizontal force which will just cause the object to move up the plane if the coefficient of friction is 0.4. Okay, please don't mind my diagram. Alright, so you know the basic things that will happen to the object. Okay, these are the natural things that will happen to the object. The object will have mg sine theta right here. This mg sine theta is the component of the weight that slides the object down the inclined plane, and this is the reason the object slides down the inclined plane. Every time you place it on an inclined plane, it slides down. It is due to the component of its weight. Okay, and the acceleration with which it slides down, the acceleration is equal to g sine of theta. Okay, alright, so that is if the surface is a frictionless surface. The acceleration is independent of the mass, but it depends on the angle at which the surface is inclined. Alright, so for this question, then we will also have the vertical component of the weight, which is mg cosine of theta. These are the natural things that will happen to the object on the inclined plane, and this is the normal force. Okay, now let's see if there is a force, and this is angle theta. Okay, now the object has a mass of 10 kg, so it means that mg, which is the weight of the object, mg, that will be equals to 10. Let's say g in this case is 9.8, so we'll have 98 newtons as the weight. Okay, and the angle theta is given as 60 degrees to the horizontal. Notice the horizontal. If the angle is 60 degrees to the vertical, that means you will be given this angle. Okay, and in that manner we need to subtract 90 from that angle to get angle theta in this case. Okay, now we need a force, an horizontal force. Now this is the horizontal force. Okay, this is the horizontal force. Let me draw it right here. This is the horizontal force. Let's say it is P. It is the horizontal force. Notice the direction, horizontal, not vertical, not along the plane. Okay, so this is the horizontal force which will cause the object to move up the inclined plane. Notice the arrow, it is towards the object. It's ready to move the object up the inclined plane. Now, but there is nothing we can do with this force right here. We need to resolve it into this manner, that is the vertical component. If I resolve it right here, that means I will have it here in this manner with its arrow in that same direction, and then I will also resolve it down right here. Okay, now notice that the angle here is the same thing as the angle right here. It is also the same thing as angle theta, because they are alternate angles. The way they look, the way they appear alternate. So this is alternate angle. When there is an angle theta right here, there will also be an angle theta right here. They will be equal to each other. So this horizontal force P, the line P, and then the base of this triangle forms this side. So this is the force P, and then this is the base of the triangle. Okay, so it forms a right angle triangle, and this is the surface of the inclined plane right here. So it forms the alternate angles. So this is, let me say this is py and this is px. Okay, so for the diagram to be neat, I may draw px in this place as well. Okay, all right, so it is the same, as you just need to know that px and py in this case, what I actually have in that place, in that diagram, is something of this nature. I have an horizontal force which is referred to as P, acting on a particular object, and I want to resolve it into this component, which is referred to as the horizontal component at an angle theta, and then I want to resolve it into its vertical component, which is py. Okay, so py in this case, it's a triangle. Okay, so if I resolve this onto this point, then I will have p cosine of theta. You need to be vast in resolving vectors. If there is an angle theta right here, then it takes cos, then this will become p sine theta. Okay, if you don't understand resolution of vector, check the video up here. The video will be suggested up here. All right, so that is it about that. Now let's solve. Okay, so px will become, and then py as well, so that we'll have px as p cos theta, and then py as p sine of theta. Notice that p cos theta is along the inclined plane and is able to push it up. Okay, it's just a component of p, of force p, while p sin theta is also a component of force p, but the force that is required in the question is force p, which is able to cause the object to move up the inclined plane. Okay, so we'll have something of this nature. Let's have the free body diagram of the object so that we will be able to identify the number of the external forces acting on the object. So notice that as p cos theta faces up the inclined plane so that it is able to drive the object up the inclined plane as a component of p, there will be a frictional force which will be ready to oppose it. Okay, the frictional force, let's say that is Fr. Okay, Fr in this manner, it is able to oppose p cos theta. All right, that means for, I'll call this axis, I'll refer to this axis as the x-axis, and then I'll refer to this axis as the y-axis. Okay, so forces on the y-axis of the object, we have the normal reaction, and then the, notice the arrow because it is a vector, so, and then we have p sine of theta. Okay, this is referred to as the positive y-axis, and I will be referring this point as the negative x-axis. So why this will be positive x-axis. Okay, and then this will be the negative x-axis. All right, so down this I'll have mg cos theta. Notice that I did not include w right here. I did not include w right here because I did not include it because I have already resolved it into its vertical and horizontal component, so there's no need to include it. All right, so I'll have something of this nature: mg cos theta, and then n, and then p sine of theta on the vertical axis. And then for the horizontal axis of the object, which is the x-axis, I'll have the frictional force Fr in this direction, and then I'll have mg sine of theta. Notice that the direction of Fr, which is the frictional force, is determined by the direction in which the object tries to move. For this question, we need a force that will cause the object to move up the inclined plane. That means the object must try to move up the inclined plane. And if the object tries to move up the inclined plane, there must be a frictional force that will oppose it, that will be down the inclined plane. Okay, so there is an angle theta right here. And then this is up the inclined plane with what? P cos theta. Notice that on this free body diagram right here, I did not also include force P because I already resolved force P into its vertical and horizontal component. So I tried this is a simplified version of the diagram. Let's find the summation of the forces on the y-axis. For the forces that are acting on the y-axis, they are balanced. Why? How do I know they are balanced? Because the object does not move along the y-axis. The object is not moving along the y-axis. It means they are balanced. There is no acceleration on the y-axis. Notice that according to Newton's second law of motion, net force is proportional to acceleration, and that's why net force acting on an object is always equal to ma, where m is the constant. Okay, so if there is no acceleration, that means the forces are either balanced or there is no force at all. Okay, that means the vector sum of the forces acting on that object is equal to 0. So that means that there is no acceleration. Okay, for the forces that are acting on the y-axis, there is no acceleration because it is not recorded in the question that the object jumps the object is jumping on the inclined plane, so that we'll be able to record the acceleration on the inclined plane. So to express that mathematically, we can say that the summation of the forces on the y-axis is equal to 0. Actually, it is supposed to be equal to ma, because there is no acceleration on the y-axis. I make it as ay as a symbol for the acceleration on the y-axis component. So because there is no acceleration on that place, so then we have the mass multiplied by 0, okay, multiplied by 0, which is actually equal to 0. So we need to add the object, the forces together. We need to do the vector sum of the forces, okay. So vector sum means that I will add the objects with their direction. N, which is the normal force, is along the positive y-axis. Yr sin theta is along the negative, no, P sin theta is along the negative y-axis. Check the arrow. And then mg cos theta is also along the negative y-axis. Okay, and that's supposed to be equal to 0. Okay, so this is the equation 1 of the problem. Remember that equation 1 is given as plus n then minus p sine of theta because of its direction, then minus mg cosine of theta, which is actually equal to 0. Okay, because the body is not accelerating along the vertical axis. So this is the equation 1. Now to find the other equation of the object. Now for the object to be accelerated up the inclined plane according to the question, it means that p cos theta, it has to be greater than or equal to the summation of the forces on the opposite direction, which is fr plus mg sine of theta. Okay, so this is the equation 2. All right, so for the object to move upward, this inequality must hold. P cos theta must be greater than or equal at the point of that equality is the minimum point, is the minimum value of P, which will be able to take the object upward. So there can be more forces when applied will still be able to take the object upward, but at that point where it is equal is the point where it is ready to set the object up. All right, so but we need to find an expression for fr. Recall that fr is equal to mu n, but notice that we can get an equation for n from equation 1 by making n the subject of the formula, so that from equation 1 n will become p sine theta plus mg cos theta. I did this by adding p sine theta to both sides in equation 1, so that fr will become mu into p sine of theta plus mg cosine of theta. So upon distribution of mu, I'll have mu p sine theta plus mu mg cosine of angle theta. Alright, now p can be substituted into equation 2, so that equation 2 will become p cos theta greater than or equal to fr, which is now mu p sine theta plus mu m cos theta, okay, plus mg sine of theta. Now to make p the subject of the formula, we may take mu p sine theta to the other side, so that we'll have, before that we can divide through by cos theta. If we divide through by cos theta, then we should have something of this nature: cos theta, then cosine of theta, cosine of theta. Okay, so that cosine of theta cancels out right here, and notice that sine upon cos is actually equal to tan of theta, so that P is greater than or equal to mu P tan theta plus, this is actually mu mg, so there is g right here from this point mg. Okay, so plus mu mg plus mg tan of theta. All right, so by taking mu p tan theta to the other side of the inequality, so that we'll be able to make p the subject of the formula, then that will be p minus the mu of p tan theta, which has to be greater than or equal to mu mg plus mg tan theta. Okay, so by p being common into 1 minus mu tan theta, and then greater than or equal to mu mg plus mg tan theta, so that by making p the subject of the formula, p will be greater than or equal to mu mg plus mg tan of theta upon 1 minus mu tan theta. I got this inequality by dividing both sides by 1 minus mu tan theta, which we will arrive at this. So for simplicity, mg is common to both sides of the numerator, so that I will have mu plus tan of theta upon 1 minus mu tan theta. So we can substitute the values so that we'll be able to go further. All right, p will be greater than or equal to mg. Notice that m is 10, and then g, in this case let's use 9.8, into mu, where mu is 0.4, then plus tan of 60 degrees, okay, upon 1 minus 0.4 multiplied by the tan of 60 degrees. So we should have 208.94 at the numerator, then 1 minus 0.4 multiplied by tan of 60 degrees at the denominator, which is actually equal to 0.31. So if you do this division, 680.1 or 680.2 Newton. Okay, so it means that P has to be greater than or equal to 680.2 Newton. So the point where P is equal to 680.2 Newton is the minimum force. 680.2 Newton is the minimum force which is able to push the object up the inclined plane. Any force below 680.2 Newton will not be able to push the object up the inclined plane, but forces from 680.2 Newton upward will be able to push the object up the inclined plane. This is a more precise answer. You understand? So, but if it's an optional question, if you have this in the option, then you go with this as well. But I hope you understand that the force that are able to move the object up the inclined plane start from 680.2 Newton upward. So it's not confusing. Alright, let's solve the next practice problem. Determine the magnitude of the minimum horizontal force required to maintain a box of weight 20 Newton when placed on a rough inclined plane at an angle of 30 degrees above the horizontal. Rough inclined plane means an inclined plane with friction. Okay, we need the minimum horizontal force. This question is similar to the question we solved, the question 1, where 680.2 Newton is the minimum horizontal force. Okay, so in this case we don't need the greater than sign, we just need the equality sign, and which actually indicate the minimum level, that is the lowest amount of force that is able to push the object upward for that question one. But for this question we just need a force that will maintain the box, not a force that will take the object up the inclined plane like the first question. So let's go ahead. Let's say this is the inclined plane. So the object, when placed on this inclined plane, is a rough inclined plane. The object slides down. It tries to slide down the inclined plane due to mg sine of theta. Okay, now notice that we need to apply a force just to stop it, but the force is not taking the object upwards and is not taking the object downward. So if we apply a force Fr on this object, let's say we apply it, it has to be in this direction, okay, because it will be able to stop it if it is in this direction. And let's say it's in this direction, then it will add to the downward motion of the object, but it has to be in this direction. But it is not actually taking the object up the inclined plane, it is just maintaining the object, it is just stopping the object, let's say, and it is an horizontal force. Okay, so that means it needs to come from this direction, horizontal, an horizontal force, let's say P. Okay, notice that P can be resolved into P cos theta right here, just like the other problem. Okay, and then there will be a normal force acting on the object, a normal force N, and then perpendicular also, which is mg cos theta. Okay, so what is the direction of the frictional force? Oh, there will be a vertical component of P as well, just like the other problem, which has to be P sine of theta. Okay, now the direction of the friction would be up the inclined plane. Why? Because the object, the force that is being applied, force P that is being applied, is just stopping the object. It's not pushing the object up the inclined plane. So the object still tries to come down the inclined plane. Since the force that is applied is not taking it upward, so the object still try to maintain its initial movement. Its initial movement is due to mg sine theta, which actually takes it down the inclined plane. So the object still want to come down the inclined plane, irrespective of the force that is being applied to maintain it. And friction opposes the motion in which an object tries to move. So if the object tries to move down the inclined plane, then the friction will move up the inclined plane. So we can have the free body diagram right here. So this is the positive y-axis, just like we have initially. So the positive y-axis, which is the N, and then there's another force which is acting negative y-axis, and that's supposed to be P sine theta. I think we should just go straight to that, since I already explained the other time. The difference between these two, this problem and the other problem, is the direction of the friction. Okay, so the forces on the y-axis will be balanced because the object is not moving along the y-axis component. So we will have something of this nature: plus N, then minus P sine theta minus mg cos theta. It has to be equal to 0. And you know what we used to do? The only thing we need to make our subject of formula here is the N, which will be equal to P sine theta plus mg cos theta. So let's say this is the equation 1. at the minimum level, at the minimum level it has to be equal to, okay? So at the minimum level with which P will be able to maintain the object, that means P cos theta has to be equal to mg sine theta. But in this case, the friction is opposing mg sine theta, so we have Fr. It's just like having something of this nature. P cos theta, let's say this is the positive x-axis and this is the negative x-axis. Okay, so we can say that plus P cos theta plus Fr, then minus mg sine theta equal to 0. You can make P cos theta subject of the formula. P cos theta will be equal to mg sine theta minus Fr, which is still the same thing as what I have here. So that's the idea. So the equation 1, the equation 2 will be, this will be equation 2. Okay, so what we actually need is for P. So we need to substitute an equation for Fr. Recall that Fr is mu n, where n is given in equation 1 as P sine theta plus mg cosine of theta. Okay, so that Fr is equal to mu P sine of theta plus mu mg cosine of theta. Alright, that means we can actually substitute the equation for Fr into equation 2, so that equation 2, which is for P cos theta, will be equal to P cos theta then mg sine of theta minus Fr, where Fr is mu P sine theta. Oh, this is minus, so I need to be very careful. I need to make use of the bracket. Then plus mu mg cos theta. Okay, so if I distribute minus, then I'll have mg sine theta minus mu P sine theta minus mu mg cos theta. Okay, this is P cos theta. So guess the next thing. The next thing is to divide through by cosine of theta. Cosine of theta, cosine of theta, cosine of theta, cosine of theta. So cancel cosine, so that P will be made the subject of the formula, and then P will be equal to mg tan of theta minus mu P tan of theta. Okay, then minus mu mg. So if I make to make P the subject of the formula, I need to take this to the other side, so that I will have P plus mu P tan of theta is actually equal to mg tan theta minus mu mg. Okay, so I hope there is no problem. Okay, I think it's correct. So that P is common, so that I'll have 1 minus mu tan of theta, which is equal to mg tan theta, then minus mu mg. Okay, so that P is equal to mg tan theta minus mu mg upon 1 minus mu tan of theta. So mu mg is common to both sides, or that means P is equal to, okay, let me get rid of the space. P is equal to mg is common in the numerator, tan of theta minus mu upon 1 minus mu tan of theta. So upon substitution, mg which is the weight of the object, is equal to 20 newton. Then tan theta, theta in this case is 30 degrees, then minus mu, mu in this case is 0.2 upon, okay, upon 1 minus mu, which is zero point 0.2, then tan of 30 degrees. Alright, so that we'll be able to find P this way using the calculator. So upon your calculator, you can punch tan of 30 degrees, then minus zero point 0.2, which is about 0.37 multiplied by 20. So on the numerator, we'll have something of this nature, 7.547. Okay, 7.547 at the numerator, then zero point 0.2 multiplied by the tan of 30 degrees, okay, which is root 3 upon 15, then 1 minus that answer, which is equal to 0.884. That's 0.8845, so we may say 0.885. So we can have 7.547 upon the initial answer, which is equal to 8.59. Oh, I think there is a problem somewhere. Oh, this is supposed to be positive. P plus mu, P tan theta, that's supposed to be plus. So if P is common to both of that side, that's supposed to be plus. So that means we will divide through by P plus. We will divide through by 1 plus mu tan theta, which is plus right here as well. That means we need to have plus right here and then plus right here. So the denominator, there will be a change in the denominator. So that we'll have something of this nature. 0.2 multiplied by the tan of 30 degrees, then 1 plus the answer, okay, which is supposed to be 1.11547, and then 7.547 divided by that's supposed to be equal to 6.76 newton. So 6.76 newton is the minimum horizontal force that is applied right here, okay, that is applied right here to the object, which will prevent it from sliding down the inclined plane. Okay, now let's solve the next practice problem. A block of mass 0.2 kg starts up an inclined plane of 30 degrees to the horizontal with a velocity of 12 meters per second. If the coefficient of sliding friction is 0.16, determine how far up the plane the block traveled before stopping. So let's have the diagram right here. Okay, this is the object. Then naturally it will slide down the inclined plane with mg sine of theta. Okay, and then let's see at an angle of 30 degrees, so angle theta is actually moving up the inclined plane with an initial velocity. Let's say the initial velocity is u, initial velocity of 12 meters per second. Okay, so that means the object tends to move upwards. If the object tends to move upward, then there will be a frictional force that will be opposing it, which will be downwards. Since it has a sliding friction, that means the surface is a frictional surface. Okay, so we want to find the distance at which the object moves up the inclined plane. So we need the distance s from this point right here to this point. Let's say it is distance s. Before, notice that the question says determine how far up the block traveled before stopping. That means If the initial velocity is 12 meter per second, the final velocity, let's say v, is equal to 0. All right, so we may find that using the equations of motion. Recall that the equations of motion, v squared equal to u squared plus 2as. Okay, we want to make use of it as a vector equation where this side of the inclined plane is the positive x-axis, and then this side of the plane is the negative x-axis. Okay, all right, so v squared, that means the object moves upward, then v squared, v is 0, so we have 0 squared equal to u squared, that's plus 2as. In this case we don't know a yet, because we are yet to find the acceleration with which the object moves up the inclined plane. We are looking for s. I think it would be right to find the acceleration. Okay, before we continue now, to find the acceleration of the object, if the object moves up the inclined plane, then there will be a frictional force down the inclined plane, and remember that mg sine theta is also down the inclined plane. So the summation of the forces on the x-axis of the object will be equal to negative mg sine theta, since we are using down the inclined plane as the negative x-axis, then minus fr, it has to be equal to ma. Okay, where m is the mass of the object and a is the acceleration. All right, so but we need to find an expression for the frictional force. How do we get that? Notice that there will be a normal force n, and then there will be a vertical component of the weight, which is actually mg cos theta, as we have proven in the initial problems, so that n will be equal to mg cos theta. Okay, the forces on the vertical axis is balanced, only n and mg cos theta we have. Okay, or if you don't understand it this way, you may say that this is the positive y-axis and this is the negative y-axis. So the implication is that plus n then minus mg cos theta will be equal to 0, or will be equal to ma, where a is equal to 0, which is the same thing as 0. Okay, it's a is 0 because the object is not accelerating along the y-axis component of the inclined plane, so that n will be equal to mg cosine of theta. But notice that fr is equal to mu n. That means mu multiplied by n, which is mg cosine of theta. So if I substitute it in this equation, let's say this is equation 1, then equation 1 will become minus mg sine theta minus fr, which is mu mg cosine of theta, and that's supposed to be equal to ma. If I divide both sides by m, I'll have something of this nature: m, m, m. So m cancels out. The acceleration is always independent of the mass of the object. So by making a the subject of the formula, the acceleration will be equal to negative g sine of theta, negative mu g cosine of theta. So we can have something of this nature: minus g into sine of theta plus mu cosine of theta. Okay, is the equation for the acceleration. Now that means the acceleration in this case is equal to negative g sine of theta plus mu cosine of theta. So if we substitute into this equation, the acceleration is actually negative. It means that the object is decelerating, and of course it is truly decelerating since its initial velocity is 12 meters per second and is going to rest where the final velocity will be equal to 0. So the object is actually decelerating. Now to find the distance, remember that we have 0 squared equal to 12 squared, where 12 squared is 144, then plus 2a, where a is the equation of the acceleration, which is minus g into sine of theta plus mu, then cosine of angle theta, then multiplied by s. So if I take this to the other side of the equation, I will have something of this nature. The minus sign would have cancelled out, so that I will have 2g into sine of theta plus mu cosine of theta, then s, which is equal to 144. Then by dividing both sides of the equation by 2g into sine of theta plus mu cosine of theta upon 2g into sine of theta plus mu, then cosine of theta, so that eventually s will be equal to, okay, sine theta, which is the sine of 30 degrees, okay, plus mu, where mu is 0.16, okay, multiplied by cosine of 30 degrees, okay, and that's supposed to be equal to 0.6385. So I will have 2 into 9.8 multiplied by 0.6338. Okay, so if we multiply 0.6385 by 9.8 and then by 2, that will be equal to, that means s will be equal to 144 upon 12.516, which is equal to 11.5 meters. Okay, so 11.5 meters is the distance up the inclined plane with which the object decreases in is the distance up the inclined plane. So for the second problem, if the block returns, what is its speed when it gets to the bottom of the plane? The only difference here is that if the object returns, that means the object now slides down the inclined plane. The object now slides down the inclined plane, and if the object now slides down the inclined plane, it means the frictional force will be up the inclined plane. So the only difference is just the direction of the frictional force. Okay, so I just need to erase this friction right there. Okay, so we'll have something of this nature. That means the equation of the acceleration will be affected. Alright, so let's have the equations again. So on the y-axis, I already explained n will be equal to mg cosine of theta, and then on the x-axis we will have something of this nature: fr, that is plus fr, then minus mg sine of theta, it has to be equal to ma, but notice that fr is equal to mu n, so that I can make fr the subject of the formula mu n, so that it becomes mu mg cosine of theta. So by substitution we have mu mg cosine of theta, then minus mg sine of theta equal to ma. That is, I substituted this right here into this equation. If this is equation 1, then I substituted fr, which is mu mg cos theta, into equation 1. Alright, so that I will have something of this nature: divide both sides by m. If I divide both sides by m, then I will have this right here: mu g cos theta minus g sine of theta equal to a, so that a will be equal to, so we may do the multiplication. Mu is equal to 0.16, then g is 9.8, then cosine of angle 30 degrees minus 9.8 sine of 30 degrees. Okay, that will be equal to the acceleration of the object. Alright, so that's supposed to be 0.16 multiplied by 9.8 multiplied by the cosine of 30 degrees, which is equal to 1.357 minus 9.8 sine 30 degrees, which is equal to minus 3.5. So that's equal to minus 3.54. So the negative sign shows that the acceleration is down the inclined plane, that is along the negative x-axis. So that's what it means. Now we may now find the distance. So the final velocity of the object is minus 9.02 meter per second, where we can say that the magnitude of that velocity or the speed is 9.02 meter per second. Okay, so the velocity, speed is a scalar quantity. It is irrespective of the direction, so we can omit the negative sign. But talking about the velocity is 9.02 meter per second down the inclined plane. Down the inclined plane, we have represented this as negative x-axis, while we represent up the inclined plane as positive x-axis. So that is the speed of the object when it gets to the bottom of the plane. Alright, let's solve the next practice problem. A block of mass 62 kg is sliding down a snowy slope 45 degrees to the horizontal at a constant velocity. Find the coefficient of kinetic friction for the box if friction is known to be 45 Newton. Sliding down, the object is moving down the inclined plane, so it slides down with mg sine theta. If the object moves down the inclined plane, that means there will be a frictional force that will oppose the motion, which is Fr. Okay, there is no force recorded. Alright, so then there will be a normal force now, which is supposed to be mg cosine of theta, and then the other normal force, which is n, the normal. The frictional force here is given as 45 Newton. At the y-axis component of the object, n is equal to mg cos theta for reasons that I already explained. And then for the x-axis component of the object, okay, the net force, that will be, notice that summation fx is also referred to as the net force along the x-axis. And according to Newton's second law of motion, net force is equal to the force in the direction of acceleration minus the force that is opposing it. The direction of acceleration is down the inclined plane because the object slides down the inclined plane. So force in that direction is mg sine theta. And then the force that is opposing it is the friction. So we subtract from the friction, and it has to be equal to ma. But notice that the object slides down with a constant velocity from the question. If an object slides down with constant velocity means acceleration is equal to 0. Okay, that's the implication. It means that the acceleration of the object is 0. That means we are going to have mass multiplied by 0. Net force on the x-axis will be equal to 0, that is mg sine theta minus Fr equal to 0. So by adding Fr to both sides, I'll have Fr to be equal to mg sine of theta. Okay, now notice that Fr is equal to mu n, and then where mu is the coefficient of kinetic friction, and this is given as 45. So we may go ahead by substitution. Fr is 45 Newton, and then the mu, and then the normal reaction. The normal reaction is given as mg cos theta. Okay, so if I divide both sides by mg cos theta, I'll have something of this nature: mg cos theta. Okay, so that upon division, mu is equal to 45 Newton upon mg cosine of theta. Okay, now mg, which is the weight of the object, that will be, since the mass of the object is 62 kg, let's say g, which is a constant, let's say it is 9.8, and then multiply by the cosine of the angle. The angle in this case is just 45 degrees, so I think this is as simple as possible. Newton. 0.1 is a constant and it has no unit. That's the coefficient of the kinetic friction. A box slides down a plane 8 meters long that is inclined at an angle of 30 degrees with the horizontal. If the box starts from rest and the coefficient of friction is 0.25, find the acceleration of the block, its velocity at the bottom of the plane, and the time required for it to reach the bottom. So let's have the inclined plane right here. Okay, so let's say this is the object, this is the box, and of course it will slide down naturally with mg sine of theta, and then there will be a component of its weight, which is also mg cos theta, and then the normal force, which is n. So let's see the direction of motion of the object. A box slides down. That means for this question, the object is actually moving down the plane. So that means there will be a frictional force that will oppose the motion of the object, Fr. Okay, so the distance along the plane is given as 8 meters. Let's have that right here as d is equal to 8 meters, and the angle theta is 30 degrees. Okay, if the box starts from rest, that means the initial velocity of the box is equal to 0, and then the coefficient of friction is 0.25. To find the acceleration of the box along the inclined plane, it means we will consider the forces along the component of the object. The forces along the vertical component of the object are balanced, that is n is equal to mg cosine of theta, and then along the x-axis component of the object we will have forces in the direction of motion, mg sine theta, minus force that is opposing it. That is actually the definition of net force, and it has to be equal to ma. So this is the acceleration that we want to find. Now notice that Fr is actually equal to mu of the normal reaction. Then the mu, given the normal reaction as mg cos theta. Okay, so by substitution into this, we will have something of this nature: mg sine theta minus fr. Fr is mu mg cosine of theta, and that's equal to ma. So the next thing is to divide through by the mass. If I divide through by the mass, I'll have something of this nature: mass, mass, and then mass as well. So I'll have it in this manner, the mass of the object being divided. So eventually I'll have so I mean g sine theta minus mu g cos theta. The acceleration is always independent of the mass, so I think this would give the acceleration of the object. So the acceleration will be equal to g. Let's say g is 9.8, so we'll have 9.8 multiplied by the sine of theta, that is the sine of 30 degrees, minus mu is given as 0.25, then multiplied by g, where g is also 9.8, and then the cosine of angle theta, that's cos 45, that's cos 30 degrees. Okay, so eventually we'll have sine 30, which is supposed to be half, multiplied by 9.8. Okay, that's supposed to be 4.9 right there, minus 9.8 multiplied by the cosine of 30 degrees, then multiplied by 0.25. Okay, which is supposed to be about 2.12, so we can just have 2.12, then 4.9 minus that answer, that's about 2.778 meter per second squared. So this is the acceleration of the object as it slides down the inclined plane. To find the velocity at the bottom of the plane, then we need to, that means we will find the final velocity in that instance. That means to find the final velocity, we can make use of the equations of motion: v square equals to u square plus 2as. Notice that u is actually equal to 0. U is the initial velocity, v is the final velocity, a is the acceleration, and s is the distance along the inclined plane. So to find the final velocity, v squared, that's 0 plus 2a in this case, which is the acceleration, that's 2.778, and then s is the distance. The distance along the plane is given as 8 meters, so that v squared is actually equal to 2.778 multiplied by 8 multiplied by 2, and that's of course equal to 44.448. Okay, that's 44.448. So the square root of both sides will yield 6.6. Okay, that's 44.448. So that was of course equal to 6.67 meters per second. So that is the velocity down the inclined plane. Alright, let's find the time that is required for it to reach the bottom of the inclined plane. Notice that we may use this formula. It is an equation of motion formula. I derived these formulas in this video. You can check it up here. Okay, you can make use of v equals to u plus at, since it has time. Okay, so notice that the final velocity u is given as 6.67, and then u is actually equal to 0, the initial velocity. The acceleration is 2.778, and then time. So it means that 6.67 is actually equal to 2.778 t. So we can divide both sides by 2.778 2.778, so that we'll have something of this nature. t equal to, okay, 6.67 upon 2.778. So upon your calculator, we'll have something of this nature. 6.67 divided by 2.778, which is actually equal to 2.4. So the time in seconds is 2.4 seconds. Okay, 2.4 in seconds. Alright, so that's the time taken for the object to reach the bottom of the inclined plane. This is the velocity, and so that's how to work with it. You just need to find the acceleration considering the instance along the inclined plane. So I'm making use of the equations of motion. You can check my videos where I also use the equations of motion to solve linear problems.